Look at the marketing for any modern large language model, and you will see a specific number heavily advertised, the context window, 1 million, 2 million tokens. The assumption is that by giving an AI an infinitely expandable void to hold text, complex reasoning naturally follows. But under the weight of real enterprise logic, that void shatters entirely. The operational data reveals a stark reality. When organizations take massive frontier models out of experimental sandboxes and put them into enterprise production environments, an estimated 95% of these autonomous AI pilots completely fail. These models possess extraordinary raw intelligence, but they succumb to the context gap. A baseline model lacks institutional memory. It ignores specific corporate compliance rules, unwritten standard operating procedures, or nuanced decisions in Slack threads. Without this highly specific precedent, agents hallucinate or output generic, unusable advice. The reflex reaction from developers is to try and close this gap by blindly dumping massive amounts of unstructured corporate data into those massive context windows. But treating an LLM like an infinite text dump actively degrades its accuracy. Relying on unstructured, infinite context windows leads to cognitive collapse. If we want AI agents to operate autonomously and reliably, we need a rigid, systemic method to govern exactly what they are looking at. This failure has forced a distinct architectural pivot in how we build autonomous workflows. The era of relying on prompt engineering is over. Prompt engineering is a linguistic exercise. It relies on tweaking syntax, designing static personas, and formatting instructions to coax a specific response from a single query. That works well for simple tasks like translation, but it is inadequate when an agent needs to execute multi-step logic in a fluid environment. The immediate replacement discipline is context engineering. Instead of treating the context window as a bottomless bin for text, a context engineer treats it as a heavily constrained, highly volatile computational resource. This table illustrates the operational dimensions of both approaches. While prompt engineering focuses on linguistic precision for a single static interaction, context engineering is about data architecture. It manages the system-wide flow of dynamic, multi-turn information. It requires building pipelines that make micro-decisions in real time, determining exactly what data the model retrieves from external databases, how it processes that data, and crucially, what data it immediately discards. If prompt engineering dictates how a model should think, context engineering rigorously dictates what it is permitted to know at the exact moment of inference. To understand why prompt engineering breaks in long sequences, we have to look directly at the mathematical mechanics of the transformer architecture itself. This equation shows the standard self-attention calculation. Notice the n sequence length variable. As n grows, and as relative positional encodings kick in, the model naturally anchors its focus heavily on the absolute beginning and the absolute end of a text block. This creates the lost in the middle phenomenon. As the sequence length grows exponentially, the probability mass thins out. The model's attention spikes at the boundaries, leaving a deep dip right in the center of the text. This probability dilution leads directly to context rot and agent amnesia. The tokens sitting in that middle zone suffer a severe drop in their signal-to-noise ratio, and the data there is effectively ignored. Every single token you add to a prompt acts as a direct tax on the model's finite attention budget. There is no such thing as free context. This leads to a harsh operational reality. Adding more raw, marginally relevant documents to your prompt pushes critical facts into that low-attention middle zone. The math demonstrates that dumping unstructured data into an LLM compromises its reliability. By prioritizing noise over signal, builders force the model to reason across a degraded information environment. To defend the attention budget, system architects use a governing principle called minimum viable context, or MVC. The rule is absolute. At any given computational step, the model must receive exactly the tokens it needs to compute the next action, and absolutely nothing more. To execute MVC in production, engineers organize data using a design pattern known as the context pyramid. The structure is divided by volatility. The base layer is packed with static, persistent knowledge, safety policies, overarching goals, and strict formatting rules. The dynamic middle layer houses temporary, retrieved memory for the current step, and the tiny peak is reserved exclusively for ephemeral state. the immediate user query, or a raw tool output. By maintaining this strict hierarchy, the context pyramid permanently segregates static enterprise rules from chaotic, real-time observational noise, preventing context rot before it starts. Populating that dynamic middle tier with accurate information requires moving beyond simple semantic search. Standard vector RAG plots text chunks in a high-dimensional vector space. That works for basic factual lookups, but if an autonomous agent needs to trace multi-hop dependencies or relational logic, high-dimensional semantic matching collapses. There are no clear paths between unrelated terms. To solve this, engineers replace vector guessing with graph retrieval-augmented generation, utilizing structured knowledge graphs. GraphRag extracts specific topological subgraphs. It traverses explicit, labeled edges between distinct nodes, like moving from a dataset to an API to a personnel file, to map complete dependency chains. By abandoning semantic guessing in favor of explicit relational mapping, context engineers guarantee the LLM receives an explainable, deterministic map of reality to guide its reasoning. But even with perfect retrieval, a final architectural challenge remains. If an autonomous agent runs continuously for days, how do you maintain its operational state without the conversational transcript expanding infinitely? The structural solution to monolithic prompt collapse is a framework called Agentic Context Engineering, or ACE. ACE restructures how an agent perceives its environment and maintains its working memory. It converts free-form text transcripts into a highly structured, queryable playbook consisting of discrete, itemized bullet points, each assigned a stable ID tag. Instead of continuously appending massive new blocks of text after every action, ACE uses incremental delta updates. The system actively targets specific bullet points to edit, delete, or merge logic in place. To keep this playbook pristine, the framework deploys background routines known as the reflector and the curator, which constantly analyze the main agent's execution logs. The curator routine applies semantic similarity algorithms to actively deduplicate redundant logic and systematically decay older, less relevant memories over time. The ACE framework transforms a chaotic, linearly expanding prompt into a self-curating database. It enables true long-horizon autonomy while enforcing a hard cap on token growth. In real-world enterprise environments, even with highly structured playbooks, autonomous agents will inevitably process enough raw data to quickly hit the hard token limits of frontier models. To survive these massive analytical tasks, engineers deploy server-side editing primitives, specialized algorithmic tools that intercept and compress state dynamically. Look at this context window burdened by a bloated raw JSON payload. To fix this, engineers use tool result clearing. The server surgically strips the heavy data, leaving a single tiny placeholder token. The agent retains the memory but sheds the token weight. Server-side editing allows an autonomous agent to process and analyze millions of tokens over a long workflow while keeping its immediate active context window lean. This brings us to the financial reality of deploying AI at scale. Ingesting 150,000 highly engineered tokens for every single microaction in an agentic loop incurs massive latency and prohibitive financial costs. The infrastructure-level breakthrough that solves this economic bottleneck is key-value prompt caching. By front-loading massive amounts of static context, like the thick base layer of our context pyramid, the system completely bypasses the compute phase for identical inputs, loading representations directly into memory. This chart demonstrates the financial impact of caching. A standard $3 input cost per million tokens drops by 90%, down to an effective cost of just 30 cents. Prompt caching transforms these structures from technical optimizations into financial requirements for any organization operating at scale, which leaves one final architectural question. How does this meticulously engineered context actually connect to fragmented enterprise systems securely without breaking? The industry response is the Model Context Protocol, or MCP. It serves as the universal standard for AI interoperability, essentially acting as the modular USB-C cable for connecting models to enterprise data. MCP physically separates the client AI agent from the enterprise systems it interacts with, shifting the burden of data validation and governance entirely to the server side. This animation illustrates the process. As chaotic raw data hits the MCP server firewall, the server pre-processes and sanitizes complex payloads. extracting only the high-signal entities into clean schema blocks before they ever enter the agent's context window. This architecture natively enforces strict security governance. It guarantees the AI agent's operational context perfectly mirrors the exact permission set of the human operator, mitigating unauthorized data access. The ultimate capability of an agentic system is inversely proportional to the irrelevant noise it processes. The future of AI relies not on infinitely large text voids, but on the structural precision of the data environments built around them.